Alright, in today's video we're going to learn how to solve any linear first order ODE, any kind, the most general possible. In fact, what we will do, this is going to be two videos about general first order linear ODEs. In the first one, I'm going to give you the formula that gives you the solution of any linear first order ODEs, and we're going to see not one, not two, three different ways of arriving to that formula. So we are familiar with it and we understand where it comes from and kind of get a little bit trained into logical thinking in math. Okay? All right, so first let's understand let's recall what the first order linear ODEs is. So this, what I wrote here is what I call the standard form for a first order linear ODE. And it's like that. So that you have the dependent variable, first derivative, plus some function times the dependent variable equals some function of the independent variable. All right? So you can tell that if r of t is different from 0, this would be inhomogeneous. And if r of t is 0, it's a homogeneous equation. All right. So any equation that is linear first order, ODE, can be written in the standard form. For example, I have this one here, t squared x dot plus 9x divided by 12, but that's easy. I divide by t squared everything. So I get I get x dot plus 9 divided by t squared x equals 12 divided by t. Just dividing, and what I did is divide by t squared, so times 1 over t squared, right? And then identify what is p of t. P of t in this case is 9 divided by t squared, and r of t is equal to 12 divided by t. So very easy to identify and put an equation in standard form. Any equation that is linear first order can be written in standard form. All right, so for an equation written in standard form, I'll give you the solution of the equation is the following. X of t is going to be equal to e to the minus integral of p of t dt that multiplies integral r of t e to the p of t dt, all right, dt plus a constant. All right, where the integrals here notate the antiderivatives. So this expression is what you're going to be using to solve first order linear ODEs every time. In the second, so again, this video is about deriving this formula, proving, because this is never believe what I tell you. How do you know? How are you supposed to know that, I don't know, when I was in the bathroom, when Eduardo was in the bathroom, I got him from behind, and I knocked him unconscious, locked him up, or maybe even killed him, and then I'm telling you lies instead of this. Well, the nice thing about math, you know what it is, that even if I'm lying, you can check if what I'm telling you is true or not, because you're gonna see proofs. So you should be able to prove the statements that I give you. So if the proof checks out, I'm not lying to you. Even if I were lying, you know you have the truth, because you have a proof. And we will be doing the proof. Never believe things that are not proven to you. And when I tell you something without proof, I will tell you where to find the proof and where it comes from. Because there's maybe a couple of tiny points where I give you theorems without a proof, but I will tell you where to get it, because you should never trust people that tell you should never trust the math you pick on the streets, all right? You should be able to check the proofs. All right, so this is the expression, and the second video that we do about this is going to be about applying it to examples, of course. But in this video, it's about deriving this, proving that this equation, the solution of this equation is this one. We're going to prove it in three different ways. And they are three different historical ways. So we're going to follow on the steps of the people who first proved them, who first actually found solutions to them. All right, so let's do the first one. The first one is actually from the Bernoullis. So let's erase the board, move this formula to someplace handy, perhaps there, and see what happens, and then start proving this formula in three different ways. All right, so we have this. We need to prove that this is the general solution to this, and we're going to see the first method that was actually historically the first one that was found, that is subscribed to the Bernoullis. So what we do to solve this is, okay, how about we rewrite x the dependent variable, what we want to find, as a function, as a product of two functions, u of t and v of t. Of course, this u is where u is, of course, a u of t, and v is a v of t. So at first sight, it may look that this is actually going one step backwards, right? Because it's like, well, you had one unknown, now you have two, that they're the product. How is that good? Well, we will see, because this is going to take advantage of some properties of the derivative. So, following the Bernoullis, we rewrite equation 1. Equation 1 as a function, well, substitute, maybe rather we say substitute x equal uv in 1, and we get the following. If we do that, then we get u times, well, let's just write the whole thing, d dt of u times v plus p of t uv equals r of t. So we apply Leibniz rule here, and what we get is u dot v plus u v dot equals r of t minus p of t u v. Okay, I put this on the right hand side, the p term on the right hand side, and only the derivative on the left hand side. All right, so now we realize all the following. Since this splitting x equals u times v is arbitrary, it works for any choices. For example, I could pick v equals x, u equals 1, or v equals x divided by t and u equals t, and there are an infinitely many ways of doing that splitting, and that has to be true for all of them. Then it has to be true that all the coefficients of v on the left hand side and the right hand side, you see whatever is multiplying v has to be the same in both sides. It has to work for any form of v and u. All right, so let's equating the coefficients of v on both left and right hand side. We get that, so what multiplies v on the left? U dot. Okay, so u dot has to be equal to whatever multiplies v on the right, which is minus pt u. Minus pt u. All right, and then, of course, the rest, if this is equal to this in this particular splitting, then we know that the rest has to be equal to the rest. The rest of things that we have not considered here has to be equal to the rest of things that are not considered here. Okay, so this is a particular splitting of things, right? Because u and v are arbitrary, then we can choose u and v so that the coefficients of v are the same on both sides, and then the rest is equal to whatever is the rest on the other. So, equating the rest of terms on both sides of the equation, we get, well, here we are left with u times v dot, so we get u times v dot, and on the right is just r of t equals r of t. Right. If these two equations are true, then we know this is satisfied automatically. Agreed? So if this one is fulfilled, let's call this one 2 and this one 3. If 2 and 3 are fulfilled, then automatically this equation is fulfilled. And that means that the original equation 1 is fulfilled, because this is the same as equation 1, only with the change of variables. Hopefully we agree. Please do ask questions in our live sessions if there's something that is difficult to get. Alright, the nice thing about it though is that this equation, equation 2, is easy, right? Equation 2 is of the kind that we know how to solve. We can put the u's on one side and the p on the other side. So equation 2 is very easy. Equation 2, I can solve, and I separate it, and it's u dot divided by u equals to minus p of t. Then we integrate and we get the log. Remember how that goes? This is if you want du dt, so the dt on this side to integrate with t, and here we get du, 1 over u. We've done it already 1,000 times, so let's just get it directly. This thing tells me that, well, let me put it like this. I'll just write it, du divided by u, it's equal to minus p of t dt. And then we can integrate. If we integrate it, we get that integrate on the left, we get a logarithm. Integrate on the right, we get the integral minus p. So we get logarithm of u, it's equal to integral minus pt dt. And then we undo the logarithm by taking an exponential. I mean, technically we have to do the absolute value bars, but I'm going to get one solution only because we only need one solution for this one. We're going to ascribe the integration constants and the rest of the solutions to v. So we get that u is, one solution is that u is the exponential of minus integral pt dt. Nice. So we get an expression for u. Let's call this expression 4. All right. Nice. Now, equation 3 can also, this is for equation 2, right? Equation 3 can also be really integrated. Let's do it here. Equation 3, we have uv equals r of t, right? And then that means that v dot is equal r of t divided by u. But of course, we already computed u, so we use equation 4 in here because we've already computed what u is. And well, we don't need to use it actually at this point. We can just say that v, whatever v is, it's equal to the integral of r of t divided by u dt plus a constant. All right, but then we can substitute. Let's just substitute now equation 4. So substituting equation 4, we get that v is equal to integral of r of t, and then, well, actually, it's r of t divided by u, which is the exponential of minus pt dt. So this is 1 over the positive exponential. So let's just write it like this. So it's r of t exponential of p of t dt plus a constant, plus an integration constant. Wonderful. So we found u. This is a partial result. We found v. This is another partial result. We can put them together because the final solution is u times v. So finally, x of t, which is equal u of t times v of t, it's equal to, let's just write it. So u, the exponential of minus p of t dt, that multiplies v, which is integral r of t exponential of p of t dt plus a constant. And there we go. This is exactly the formula that we have on top of the board that we wanted to prove. It is proven. Method number 1. All right. Nice. Let's see more methods. All right. So the first method that we saw, the Bernoulli method, was historically the first one that was used. However, it tends to be the least intuitive to ECE students. So let's discuss other methods that are actually perhaps more intuitive, or at least, I don't know, give you some training into thinking mathematically of how to prove things, how to find solutions when you don't know. Imagine, nobody knows that formula. How are you supposed to find it? Method 2 is called the method of variation of constants. So it's based on the following observation. So it's based on something that is called making an ansatz. Making an ansatz is making an educated guess as to, okay, maybe the solution is of this form, and then try the solution and see if you are right. Math will tell you, oh, you're right, you actually got it right, here it is. And if you got it wrong, math will tell you, no, that guess that you had is really wrong, so no, try something else. So let's do that. This method is inspiring a lot of intuition. First is the fact that, well, I do not know how to solve 1, but I know how to solve something easier, which is x plus p of t, x equals 0, right? If it's the homogeneous version. If it's the homogeneous version, well, it's separable, right? So then if that's the case, then we know that this equation we get x dot divided by x equals minus p of t, which again is the same as dx divided by x equals minus p of t dt, which we can integrate, and we get log of x it's equal to minus the integral of p of t dt, and then we undo the log with an exponential, and we find that x of t would be equal to some integration constant. Again, rigorously speaking, we should have here the absolute value, and then this absolute value is an integration constant c. When we take exponentials, that becomes a multiplicative constant, as we saw in the method in the video of separation of variables. Please check it if this doesn't sound familiar. And then we make c be positive and negative, and we account for the two possibilities of the absolute value being positive or negative. So anyway, what we get in the end, this is also an equation that we've solved before, and this is the exponential undoes the log and creates an integration constant. That would be plus d, right? And when you take exponential, you get the exponential of this times the exponential of d, which is always positive. You call the exponential of d c, the new constant, and you let it be a real number, positive and negative, and that accounts for the two branches of the solution. Okay? X being positive and x being negative, which is what this is telling you. The log has to be equal to that works for x being positive or negative. That's why I usually don't write the log in here. I mean, as I said in the video for separable equations. If you have questions about that, please do ask. That's the reason the live sessions are there. All right. So we have p of t dt here, right? And that will be the solution. And I'll be very happy. So this represents how happy I am with the fact that I know how to solve that one. Now, right, but that's not the problem I want to solve. I want to solve that one with an RT in there. So here's an ansatz. It's like, well, they're similar, so maybe I can base the solution of this based it on the solution of this one. So let me try to generalize this a bit. Question, so ansatz. Would x of t equals c of t e to minus p of t dt be a solution of 1 for some c of t? So you don't know a priori. It's like, well, it might, right? In the sense that if I let the integration constant vary, maybe I'm accounting for the generality of having an homogeneity. Kind of makes sense, because if you plug it in here, you see, it's like, well, the exponential gives me the p with a minus that would cancel this, but then I would have, that would work if this is 0, but if it's not 0, maybe the derivative of the c will give me something that cancels. Maybe this could be arbitrary, just find one that solves it, right? It gives me more freedom to maybe cancel this r of t, getting some function on the left. So, again, you don't know if that's going to work, it's an ansatz. So, ansatz usually when you try them, math tells you, actually, yes, there is a c that does it for you, here's the c that does it for you. And if not, math will tell you, no, tough luck, no, try something else. Let's see if this guess is a good guess, and then if this guess gives me the form of c of t. All right, so what we do is we plug in, let's call this equation 2, and let's plug equation 2 into 1 and see what math tells us. So if I do that, I get the first one, right? So the first term is the derivative of the whole thing. So I have to do the Leibniz rule first. Derivative c dot, derivative of c with respect to t, times the exponential without derivation, right? And then plus, now it would be the derivative of this one times the c without derivation. Okay, the derivative of this one, what is it? Well, it's the exponential, which is the same function, but multiplied by the derivative of the argument of the exponential. So that's easy, because that would be a minus from the minus, p of t, right? The derivative of the integral of p to dt is p of t, and then c of t. The c of t goes first, of course. C of t, then p of t, and of course the same exponential, because the derivative of exponential itself. So basically, exponential of a function of t, if I take dt, right? This thing is f prime of t exponential of f of t, right? That's what I'm using. Of course, you need to remember all this, but that's what I'm using here. Minus p of t dt. All right, and then plus P of t multiplying x of t, the solution, right? Equation 2. So that would be C of t e to the minus P of t dt. And that would be equal to R of t. All right, so all this thing here is x dot, and this thing here is P of t x, and I substituted x by this equation, equation 2. Now, let's realize of something. Look at this. This term here and this term here, they are the same with opposite signs. So this thing cancels this thing. How cool is that? Well, it's pretty cool, because then the equation gets awfully simplified to the following. C dot of t e to the minus P of t dt, it's equal to, well, where is it? R of t. All right. And that means that C dot of t is equal to R of t e to the integral of P of t dt, right? Move this dividing the r, but then minus sign puts in the numerator. All right, that's wonderful, because now I can integrate with respect to t on both sides, and I get the value of the constant. C of t, C of t, it's equal, I integrate on the left, integrate on the right, I get R of t e to the P of t dt, plus an integration constant. Let's call it, I don't know, we can call it C. Why not? All right, so now we substitute these three in equation 2. So look at math. Math tells us, I plug this in into the original equation. If the answer was wrong, I would have arrived to a mathematical contradiction. So if you make a wrong answer and you put it into the equation, you find not compatible with equation 1. So go back and try something else. But not only it was compatible with equation 1, it gave me a really nice expression to find C. So math is telling me, yes, your answer was correct, and here's the form of C of t. So just substitute C of t here, and you've won. And if we do it, we get that x of t is equal to, substitute the C by the C of t. Well, I'll put this one first, okay? I put this one on the left. This is e to the minus P of t dt. And then that multiplies the value of C, which is integral R of t e to the P of t dt plus C. Well, look at that. That expression is again the expression we wanted to prove. We've won again. Method number 2 proved that the solution, the general solution to this equation is of this form. And see how we did it this time. This time we said, I know the solution of that. There's a much simpler equation, there's no inhomogeneity. Maybe the solution to the full problem is not that different from that one. Maybe just letting the constant vary will do it. Maybe not, but let's see if math tells me if I'm right or wrong, with that suspicion, with that intuition, if you want, with that guess. Then I plug it up, I make the guess that this may be the solution to the full problem. I plug it into the full problem, and math tells me, well, you're right. I mean, it's okay, yeah, you got it. That's actually correct. And here's the form of C, of the constant C that you have. And finding this form of the constant C, we found the final solution. Proved. All right, let's see yet another third method. All right, method 3, we call it find an integrating factor. So it's related to what we did for exact equations, but it's not the same integrating factor as an exact equation. What I mean by find an integrating factor is, okay, maybe I can find some mu, maybe there is a mu of t such that I can rewrite equation 1 as a total derivative equal to a function of t. What does that mean? So maybe there is a mu such that equation 1 becomes d dt, total derivative of mu of t x, equals mu of t r of t. So maybe there's a mu such that I can write 1 as this form which is 2 in this form. Would I win something if I do that? Well, yes, you would, because this is easy to solve, right? If so, the solution is easily found integrating with respect to WRT, with respect to, that's what it means. With respect to t on both sides. So if I integrate the left-hand side with respect to t, cancels the derivative, and that gives me mu of t x, and on the right-hand side, that would give me integral of mu of t x, r of t dt. And let me add explicitly the integration constant that we get out of that integration. I mean, we have one in both we have an integration constant, we can unify them into a single constant here. So we write this one without the constant, and the constant from this one we call it c. Alright, so you see, then it's very easy, because then x becomes, if that's the case, x of t becomes 1 over mu of t integral of mu of t r of t plus c. And we will solve the problem if there was a mu that does that. Alright, so nice. Let's see if we can find one. Alright. Let's call this equation 3. And let's see if we can find one. Let's multiply both sides of 1 by mu. Multiply equation 1 by mu of t. If we do that, we get mu of t times x dot plus mu of t times p of t times x equals mu of t r of t. That's what we get if we multiply equation 1 by mu on both sides. Now, let's make the following observations. The product rule tells me that d dt on the product mu x, that is equal to mu dot x plus mu x dot, right? Oh, but that also means that mu x dot, it's equal to d dt mu x minus mu dot x, right? I just put the mu dot x on the other side of the equation. Aha! So we have mu x here, and we have mu x dot here, mu x dot here. I can substitute this. Let's call this equation 5, and this one equation 4. And then what we do is substitute 5 into 4. If we do that, we get the following. d dt mu x minus mu dot x. That is this term, okay? That I substituted by this. Right, plus mu p x. I'm not writing the dependence on t because it's everything here depends on t. Px equals mu r. I just copy. This is literally this one, this is this one, this is this one, and this is this one. All right, wonderful. All right, so if we do that now, we simplify this to the following. We get that d dt multiplying mu acting on mu x plus common factor of x, x multiplying mu p minus mu dot equals mu r. All right. So now this equation, let's call it 6. And let's compare. Equation 2, what we want, again remember, if only we could write 1 as this. And then we compare with equation 6. Equation 6 is what we get when we multiply both sides by mu. We get, okay, this is fine, this is this. Wonderful. This is fine, this is this. Wonderful. This freaking thing is in the way. We don't have what we want because of this little thing here. Sad. Do we have to go home and abandon all hope? Well, the answer is no, because mu is arbitrary. We haven't chosen mu. So maybe there is one mu, one in particular, that makes this 0. If that mu makes this 0, then we won, because we have the equation originally as written exactly as we want it. So let's try to find a mu that makes this 0. Let me erase the board and let's do that. Okay, so remember, what we want is to be able to write this equation like this. Because if we could, of course, remember that I'm not writing the dependence on t, because everything depends on t here. I recover it here for aesthetic purposes. So if this is true, right, then we integrate on both sides with respect to t and find that x of t is 1 over mu, multiplying the integral of r times mu, integrated with respect to t, that I forgot to write, dt, plus a constant. Now, unfortunately, what we did, so what we got is this one. How did we get this one? Well, just multiplying by mu, the left-hand side and the right-hand side, and manipulating. We arrived to this. Unfortunately, this thing doesn't look like this one, but almost, because this is here, this thing is on the way. But maybe we can find a mu for which this is 0, and then we've won. We have it in that form. All right, so let's impose it. Let's impose that mu of t times p of t minus mu dot of t equals 0. If we impose that, this equation is of a form that we will recognize. It's a separable equation, right? So we get that mu dot of t divided by mu of t is equal to p of t, right? So again, we integrate, this is the log integral, remember it's u dot divided by u, the integral is the log of u. Then we integrate here, we get integral of pt dt, and this is a log, the log, we take exponentials to undo it. We've done this already 3 times in this exercise. So mu of t, that satisfies that, is exactly the exponential of p of t dt. This is again a separable equation, and this separable equation we solve 1,000 times, is the exponential. So we found a mu, look at that. We found a mu of t such that, I mean, of course, times a constant, but I don't care about the constant because it's just one of them. I found a in mu of t, an integrating factor such that this term is 0. Wonderful. So if this term is 0, then I know that the solution is of this form. So let's just write the solution of this form, substituting the integrating factor that we found. So let's call this now 7, and this 6, and then we're gonna do inserted 7 in 6, which we can do because this term is 0 for the particular trace 7. Remember, this term is 0, so it has exactly this form. So x is exactly of that other form. Then we get that x of t is equal to, okay, 1 over this is e to the minus that, e to the minus p of t dt, multiplying the integral of r of t, mu of t, so r of t, and then mu is exponential of p of t dt, plus a constant. There we go. And we found again the same formula that we wanted to prove. So the expression that this is the general solution of the general first order linear ODE, it's proven. All right, so we've done 3 different methods, and the 3 different methods arrive to the same conclusion, which is this is the general solution of any equation that is first order linear written in this standard form. I hope that these 3 methods are understood. This is the foundations of developing a little bit of math intuition, how to prove things, how to think around things, how to solve a problem that you don't know how to solve a priori. Now what we're gonna do in the next video It's find solutions, solve linear equations, particular examples of linear equations, and solve them applying this formula. This is what it is. You don't need to do more. Now that we proved it, we only need to apply this formula, and that's it. All right, see you in the next video.